Bravo. Oh, yeah. Good evening, everyone. Respected AC sir, respected principals for all the ZNBs of Shillong region, all the respected teachers, my dear students. Good evening, everyone. Today, uh, aduh, ini loh. Uh, okay. Good evening, everyone. Respected AC sir, respected respected coordinators for today's online classes, respected principals of all JNBs of Shillong region, respected my dear students of all the JNBs of Shillong region. So today I myself welcome Rameshwar Singh, PGT Chemistry, JNB Infant West, Manipur. I am going to take PowerPoint presentation on chemical kinetics for slow achievers. So today's our topic is chemical kinetics. So now let us see what is chemical kinetics. Chemical kinetics is chemical kinetics is a branch of chemistry which deals with the rate of chemical reactions and mechanism by which the reaction occurs. A mechanism is a series of elementary steps that accounts for the overall reaction. Now let us see what is the rate of chemical reaction. It is defined as the number of moles per liter of the reactant affecting the rate of a reaction. The first factor is rate of a reaction increases with increase in concentration of reactants. Second, rate of reaction increases with the increase in temperature. That means if we increase the temperature, the rate of reaction increases. Number three, catalyst normally increases rate of a reaction, but there are some catalysts that decreases the rate of a reaction. So here I want to highlight your catalyst is a substance which alters the rate of the reaction. The catalyst which increases the rate of the reaction is called positive catalyst, and the catalyst which decreases the rate of the reaction, that is called negative catalyst. And this negative catalyst is very few, and it is applicable only for fast reaction. There are some reaction where their rate of reaction, the rate of reaction completes within 1 second or less than 1 second. So for that, we need to add some catalyst, and that catalyst is negative catalyst. Next, number 4, rate of reaction increases with the increase of surface area of solid reactant. If your reactant is solid, then if we have taken the surface area more, then the rate of reaction will also be increased. Fifth point, for gaseous reaction, rate of reaction increases with increase of pressure. Why? Because for a gaseous reaction, if we increase the pressure, the volume will decrease. If volume decrease, obviously the concentration will be more. So that's why for gaseous reaction, rate of reaction will increase with the increase of pressure. Next, 6 point. Depending upon the nature of the reactant, the rate of reaction may be fast or slow. Comes to average rate and instantaneous rate. Now let us see what is average rate and what is average rate and instantaneous rate. Average rate is the rate of reaction over a definite. Yes, sir. Okay, sir. Earphone.
Other participants, you can now admit some others are waiting to join the meeting.
Sir, देखो बा बा hello sir
Admit all click on
admit all hello sir
yes audible now
sir admit all shall I continue sir Shall I continue, sir?
Yes, please, sir. Please, now go ahead, please. Yes.
Okay. Sir,
आप मुझको भेज दीजिए प्लान शीट उसमें चैट पे क्लिक करिए कर लेंगे
Other participants, please mute yourself, please.
संदीप बैनर्जी
Yes, Rizwan Ahmed ji, please mute yourself. Yes, please, sir. Please, now you can.
Okay, sir. Now let us come to average rate and instantaneous rate, and let us see under what condition average rate may approach to instantaneous rate. Average rate is the rate of motion over a definite time interval, and it is denoted by delta X divided by is that measured over infinitely small time interval and is denoted by this rate is denoted by 1867. And this law of mass action, it takes a great important role for determining the rate of a chemical reaction. Now let us see what the law of mass action says to you. At a given temperature, the rate of a chemical reaction is directly proportional to the product of molar concentration of reactant is raised to the power equal to the number of times its species appears in the chemical reaction. The molar concentration of the reactant is known as active mass. That means rate of a chemical reaction is directly proportional to the product of molar concentrations of the reactant with their coefficients as power. And the molar concentration of the reactant, it is known as active mass. Consider a reaction A plus B giving product. So in this reaction, A and B, they represent two different reactants, and they combine together and forming some product. Now let us see what will be the rate for this reaction. Now applying this law of mass action, your rate will be directly proportional to K. That is K, a constant called specific constant, into the molar concentration of A, denoted by A enclosed by star bracket, into molar concentration of B, that is B enclosed by star bracket. That is rate equal to K, concentration of A into concentration of B. Here small k is a constant so-called specific rate constant or velocity constant. It is called specific constant or velocity constant, and it is a measure of the rate of a reaction. The value of specific constant, it differs for different reactions. When concentration of A and concentration of B is equal to 1, means when the concentration of all the reactants are taken as 1 molar, 1 molar, then what happens? Your rate will be equal to K into 1 into 1 equal to K. So let from equation number 2, we found that your rate is equal to K. That is your specific. You may define your K. Specific constant may be defined as the rate of reaction when the concentrations of reactants are taken as unity. So whenever the reactants present in a chemical reaction, if you take all the molar concentrations of the reactants are taken as unity, then that rate will be equal to the specific constant. Now let us come to a very important rate law or rate equation. Now let us see what is the rate law. Rate law is an equation expressing the rate of reaction as functions of concentrations of all species present excluding the product. So here it is very important, the term excluding the product. So while you are expressing the rate law, you have to exclude the product. We have to include only the concentrations of the reactant. You have to remove concentration of the product. Now let us see for the reaction A plus B giving product. So in this reaction, and these two reactants A and B combine together and forming some new product. Now let us see what will be the rate law for this reaction. The rate law for this reaction may be written as rate equal to K into molar concentration of B. So let it be equation number 3, unit of rate constant small k. So this unit of specific rate constant, it takes a great important role in determining the order of a reaction. So now let us see what will be the unit of K for different uh, reaction. So your rate constant K is equal to concentration raised to the power 1 minus n time inverse. So this is, don't forget, my dear students, your specific rate constant K is equal to concentration 1 minus n time inverse. Don't forget this formula. Here, your n is nothing but it is the order of the reaction, and this order n, which is the order of the reaction, may be 0, maybe 1, maybe 2, or maybe any fractional value. So this formula K equal to concentration 1 minus n time inverse is very important. So all of you, you have to keep in your mind for determining the nature of the reaction, whether the reaction follows zero order, first order, second order, or any fractional order. Now let us come to order of a reaction. Order of a reaction. So order of a reaction is defined as the number of molecules or atoms or ions whose concentration changes as a result of chemical change. Alternatively, it may also be defined as the sum of powers of concentration terms in the rate law expression. Reactions may be zero, first, second, or third order according as order is 0, 1, 2, or 3 respectively. So let me just give if the burden of the family is carried by none of the members, neither father, mother, nor the children, then in that case, for that family, the order is said to be a zero order react, a zero order family. So, my dear children, so your order is nothing but it is the reactant. The reactant may be molecule or ion, where the rate of the reaction depends. So we have to count only that number of reactant molecules where the rate depends. So if the rate depends only on first power concentration of the reactant, in that case, it will be of first order. If second power, second order. If it is third power, third order. If it is none of the reactant molecules, there is your zero order. So order may never exceed from 3. Now let us see some examples of order of a reaction. First example is decomposition of ammonia at the surface of gold or platinum. So you have to take some ammonia at the surface of gold or platinum, and this reaction occurs at a temperature of 1130 Kelvin. So this decomposition of ammonia into nitrogen and hydrogen, while we are determining the rate, it is found experimentally that rate is independent of the amount of ammonia. So it doesn't depend on ammonia. Whether you take more amount or less amount, it doesn't affect on the rate. So that's why this reaction follows a zero order reaction. Now comes to the second example. Second example is hydrogenation of ethane. Hydrogenation of ethene. Hydrogenation of ethene to form ethane. And this reaction follows first order. Now let us see how this reaction follows first order. So the reaction occurs like this: ethene plus hydrogen, giving ethane C2I6. So experimentally it is found that your rate law is rate equal to K molar concentration of ethene rise to the power 1, molar concentration of hydrogen rise to the power 0. That means for this reaction, though there are two reactants, namely ethene and hydrogen, the rate of the reaction depends only on ethene. It doesn't depend on hydrogen. So that's why this reaction will follow fast order, though it contains two different reactant molecules. So this reaction follows fast order reaction. Now let us come to a very important topic, that is a molecularity of a reaction. Now let us see what is molecularity of a reaction. Before coming to the molecularity of a reaction, let me just remind one more important regarding the order. Your order is an experimentally determined value. It is not a theoretically determined value. It is an experimentally determined value. Molecularity of a reaction is defined as the number of reacting molecules of all substances taking part in a chemical reaction. Reactions may be unimolecular, bimolecular, or trimolecular, depending upon the number of reactant molecules involved in a reaction is 1, 2, or 3 respectively. So here also, let me just give a simple example. If a family is having 3 members, for that family having 3 members, then its molecularity is said to be 3. That is your trimolecular or thermolecular, because the family is having 3 members. If a family is having only 2 members, then in that case, that family is said to be of bimolecular. If you are alone, then in that case, your molecularity is said to be 1. So here also, molecularity will never exceed 3. Why? Because if the number of reactant molecules is small, then complexity arises. So if complexity arises, then it is very difficult to discuss the nature of the reaction. So that's why we prefer to have the molecularity only up to 3. Now let us see some examples of molecularity of a reaction. The first example is decomposition of PCl5, decomposition of phosphorus pentachloride. Phosphorus pentachloride, it decomposes into PCl3, that is phosphorus trichloride plus chlorine. So this reaction is following unimolecular. Why? Because here in this reaction, the reactant is only one more reactant. What is the reactant? PCl5. So that's why for this reaction, molecularity is 1. If the molecularity is 1, then the reaction is said to be a unimolecular reaction. Now comes to second example, dissociation of hydrogen iodide. Hydrogen iodide dissociates into hydrogen and iodine. So here there are 2 molecules of hydrogen iodide as a reactant. So that's why for this reaction, molecularity is 2. If the molecularity is 2, then the reaction is said to be of a bimolecular reaction. Yes, any problem? Now let us come to comparison of order and molecularity of a reaction. And regarding the similarity, the first point is their value do not exceed 3. Their value do not exceed 3. Your order as well as molecularity value, it will never exceed 3. Second point, their values depend upon the condition of a reaction. Now let us see the differences between order and molecularity of a reaction. In the other column, the first point is it is the sum of powers of molar concentration terms of the reactant in the rate law expression of a chemical reaction. Next, molecularity. It is the number of reacting molecules of the reactant species taking part in a single step chemical reaction. Number two, it is an experimentally determined value. As I've already said, your order is an yes, sir.
Some students are trying to join. Please.
Two. In the molecularity column, your molecularity, it is a theoretically determined value. And next, number three, your order may be a whole number, may be zero or a fraction. Next, molecularity number. Don't forget your molecularity is always a whole number. It can never be zero or a fraction value. Next, number four, it senses with a sense of temperature, pressure or concentration. If you sense temperature or pressure or concentration, that will be sensed in the nature of the reaction. Definitely, it will be sensed in the order of the reaction. Then, on the other hand,
Sir.
yes, sir.
Some more participants they want to join. Please allow.
Okay, sir. Okay, sir. Salanjan. Salanjan. Mika join tao rồi. I did. Sadam Hambi. Mika join tao. Mute. Multiple voltage. Emit on. Đi dầu rồi, đi dầu rồi. Mới đó, 오토도 하이레 해보고. 아니다, 오토도 파기다가 가야 돼요. Với tôi tông rồi, anh dân xuống tông rồi, tôi mới được, tôi tông hay apa, chứ tôi phải chỉ tông. Nào là tôi liều sai, mới tôi hay đấy, sai tôi liều. 3 over. Okay, sir. Shall I continue, sir? Hello, sir. Can you hear me, sir?
Yes, go ahead, sir. Go ahead, sir.
Okay, sir.
Yes,
Now,
yes, sir, please. Go ahead.
okay, sir. Now let us come to a very important term called pseudo-unimolecular reaction. And this pseudo-unimolecular reaction, it is also called pseudo-first order reaction. These pseudo-unimolecular reactions are those reactions which satisfy first order reaction, but actually more than one molecule is involved in the chemical reaction. So in short, these pseudo-unimolecular reactions are those reactions following first order reactions, though there are two different reactant molecules. So some two or three important examples are given in the NCERT textbook. The first example is inversion of cane sugar. So this cane sugar, there is C12H22O11. This is cane sugar plus water. And when you do your hydrolysis on cane sugar, it decomposes into glucose and fructose. C6H12O6 plus C6H12O6. Both glucose and fructose are having the same molecular formula, but containing different functional group. Glucose is a hexose and fructose is a ketohexose, as you have learned in biomolecule. So here, for this reaction, it is found experimentally that the rate is equal to K molar concentration of cane sugar. That means the rate law is found as the rate on only the first power concentration of cane sugar. It doesn't depend on the concentration of your water. So if we have already know that order is determined by this rate law. So that's why here order will be 1. Why it becomes a 1? Because the power of cane sugar is 1. So that's why here the order is first order. And molecularity is 2. Why the molecularity is 2? Because in this reaction, two different reactants are there. The first one is your cane sugar and the second one is water. So 1 plus 1 is becoming 2. Yeah, I am writing in short as 2. So here molecularity is 2. If the molecularity is 2, that is called a bimolecular. So this inversion of cane sugar is a good example of pseudo-unimolecular reaction. Is this reaction is a reaction containing two reactant molecules, but the rate depends only on the concentration of the second example is hydrolysis of methyl. This methyl acetate CH3OOCH3. This is methyl acetate plus water. So when you do hydrolysis on water, it gives acetic acid. That is CH3COOH plus methanol. So for this reaction, it is found experimentally that your rate is equal to K concentration of methyl acetate rise to the power 1. That means the rate of the acetate, it doesn't depend on water. How we know? Because it is known by performing experiment. So that's why we are just saying this rate law is an experimental. Order is 1 because in the rate law it is found that the power of concentration of methyl acetate is 1. So that's why order is 1. If the order is 1, then it is first order. And molecularity is 2. Why the molecularity is 2? Because in this reaction, two reactant molecules are there. One is methyl acetate and the other one is water. So that's why 1 plus 1 is becoming 2. So if the molecularity is 2, it is called bimolecular. So this hydrolysis of methyl acetate, it is also a pseudo-unimolecular reaction because this reaction is a reaction containing two reactant molecules, but the rate depends only on the concentration of methyl acetate, but not on water. Now let us come to zero order reaction. Now let us see zero order reaction. As I have said previously also, now let us see what is zero order reaction. A reaction is said to be zero order reaction if the rate of reaction is independent of initial concentration of reactant. So under what condition is reaction is said to be zero order? A reaction is said to be zero order if the rate of reaction doesn't depend on any initial concentration of the reactant. Then in that case, the reaction is said to be zero order. As I have said, if in a family, if there are 2 members or 3 members or 4 members, if none of the members of the family doesn't carry the burden of the family, such family we also call a broken family, and such broken family in chemistry term, it is called I equal to R naught on equation number 2. Now after that you will be getting R equal to minus KT plus R naught. So implies to K equal to 1 by T whole into R naught minus R. So let it be equation number 4. So this equation number 4 is nothing but it is the required integrated rate equation for a zero order reaction. So what is the integrated rate equation for a zero order reaction? The integrated rate equation for a zero order reaction is K equal to 1 by T whole into concentration of R naught minus R. Means you have to take the difference of initial concentrations of the reactant, initial concentration of the reactant and concentration of the reactant at any time T, and they will give the rate expression. Now let us come to the characteristics of from the from the unit of your specific constant K. If the unit of specific constant K is in the form of concentration time inverse, then from that we can say the reaction is of zero order reaction. Next comes to graphical nature. So we have concentration of R equal to minus KT plus R naught. R naught. So let it be equation number A. So if we plot a graph between concentration of R, that is your concentration of R along y-axis and T along x-axis, we shall get a straight line with a slope equal to minus K. That is K equal to minus slope and an intercept equal to R naught. So this figure shows variation in the concentration versus time for a zero order reaction. So my dear students, this graph you have to keep in your mind, because in the past paper also this by giving the this such type of your graph, you are asking to identify whether it is fast order or zero order. So as you know, in the past report you have given the graph for fast order reaction. Okay, you have to check whether in the graph whether the concentration of R is in the form of R or in the form of ln R. If it is in the form of R, then it will be of zero order. Okay, if concentration of R is plotting with time, then it will be of zero order. If the concentration of your R is plotting along with LR with time, then there will be of fast order reaction. Now let us come to C2I4, not on C2I4, not on hydrogen. Next, second example is all natural and artificial radioactive decays like. So this radium, as you know, it is a radioactive substance. This radium dissociates into radon along with your helium. So as you know, your helium, it is your alpha ray. And for this reaction, rate is equal to K concentration of Ra. Means the rate depends on concentration of radium only. Next, third example is dissociation of N2O5, dinitrogen pentoxide. this dinitrogen pentoxide dissociates into 2 molecules of nitrogen dioxide along with half molecule of oxygen. Here, the rate law is found as rate equal to K concentration of N2O5. So, my dear children, these 3 examples of fast order reactions you have to keep in your mind for your examination point of view. In your examination, it is frequently asking the definition of fast order reaction along with one or 2 examples. Out of these 3 examples given in your book, you have to give any 2 as your choice. Now, let us come to the integrated rate equation for fast order reaction. And this integrated rate equation for fast order reaction has different forms. Now, let us see. Consider a fast order reaction R giving P. So, here R is the reactant and P is the product. Now, applying law of mass reaction, we have R is directly proportional to molar concentration of R rise to the power 1. Why? The power is what? Because the reaction follows fast order. Now, implies to minus dr by dt. Means your rate you can express as minus dr by dt. Means rate of disappearance of reactant with time equal to K into R. So where K is specific reactant constant, then implies to dr by R equal to minus K into dt. Let it be question number 1. Integrating both sides. So now let us integrate both sides of 1. We have then what do we get? We will get ln R equal to minus KT plus I. So let it be question number 2, where your I is integration constant. Now, in order to take the value of your R initially, we have to take that. So how equation number 2 is becoming as ln of R naught equal to minus K into T. Instead of T, you just substitute by 0 plus I. So from this, your I is equal to ln of R naught. Now compare 3, we have ln R equal to minus KT plus ln of R naught. So let it be question number 4. So for you just do the some rearrangement. After doing a rearrangement, it is found that ln of R naught minus ln R is equal to KT, and implies to ln of R naught divided by R equal to KT. Let it be question number 5, and implies to K equal to, from this K equal to 1 by T ln of R naught divided by R, and it is further equal to, if we convert ln means to the base E. This is natural logarithm, ln to the base E. And if this ln to the base E is converted into the log log, then it will be multiplied by 2.303. So that's why 2.303 divided by T log log R naught divided by R. So let it be question number 6. So my dear students, don't forget this integrated rate equation. And another form is exponential rate equation. Now let us see. From 5, we have ln of R naught divided by R equal to K. So if you take exponential of both sides, you will get ln and the exponential, they are multiplicative inverse. So if you take exponential of both sides for the left hand side, ln will be losing. You will get R naught by R equal to E of KT. So from this, R divided by R naught equal to E to the power minus KT. Implies to R equal to R naught into E to the power minus KT. So let it be question number 7. So this question number 7 is a exponential rate equation for a fast order reaction. So R equal to R naught into E to the power minus KT. Don't forget, this is the exponential rate equation for fast order reaction. This rate equation, exponential rate equation for fast order reaction, and about your some years back. It was asking in your CBSE examination, but it is not frequently asking in the examination. But the previous integrated equation existed in the gaseous state. Here, in my existed in the gaseous state. Here, in my presentation, I am just taking the gaseous reaction A giving B plus C. Here A is the reactant, B and C are the products. The reactant A and the two products B and C are all existed in the gaseous state. And for this gaseous reaction, then their integrated equation, it is found as K equal to 2.303 divided by T log of Pi divided by Pa, and it is equal to 2.303 divided by T log of Pi divided by Pi means initial pressure and Pt means total pressure. Total pressure is given by twice Pi minus Pt. Your Pa, that is your partial pressure of reactant A. Partial pressure of reactant A, it is found as twice Pi minus Pt. So my dear children, this formula you have to keep in your mind. This is the integrated rate equation for a gaseous fast order reaction. Don't forget, I am reminding once again that K equal to 2.303 divided by T log of Pi divided by Pa, or further equal to 2.303 divided by T log of Pi divided by twice Pi minus Pt. So this formula you have to keep in your mind. So my dear children, for fast order reaction, you have to remember three equations. The first, simple integrated rate equation. Then second one is integrated rate equation at two different time intervals. And third is the integrated rate equation for gaseous fast order reaction. These three rate equations for the fast order reactions, all of you have to keep in your mind for numerical solving. Okay. Now let us come to the characteristics of fast order reaction. There are some important three characteristics of fast order reaction. Now let us see. The first characteristic is dimension or unit. As you know, for the simple integrated rate equation is K equal to 2.303 divided by T log of R naught by R. So if we consider only the dimension or only the unit, so it will remain only time inverse, because 2.303 is a number, R naught it is concentration, and R is also concentration, and concentration it will cancel and it will take a value, and taking the value of log it will also another value, so it will be only time inverse. So K equal to time inverse. So don't forget K equal to time inverse. So your K equal to time inverse. So the first one is your dimension. So for K equal to time inverse. If the unit of K So inverse, it may be in the form of second inverse. So you will get a straight line as shown in the figure, and here your slope is equal to minus k, or k equal to minus slope. So my dear children, please be careful in your textbook, in your NCRT book. It is be careful in your textbook, in your NCRT book. It is given as okay, and here the intercept is ln of r naught, and k equal to minus slope. So your k equal to minus slope, it will be the same for zero order as well as your first order. Only the difference is in the first order we have to plot ln r along y-axis. The first order reaction, if we plot log of r naught by r, log of r naught by r along y-axis and time or t along x-axis, you will get a straight line passing through the origin, and with a slope equal to k by 2.303. So these two different graphs are given in your NCRT book. So based on these two different graphs, so you may identify the order of the reaction. If the graph is t half equal to 0.693 divided by k. So what is your half-life period? Half-life period or half change time is nothing but it is the time taken during which the initial concentration of the reactant falls down into its half. Say for example, if the concentration of the reactant is 50 gram, so what is the half of 50 gram? Half of the 50. So what is the half of 50 gram? Half of the 50 gram is 25 gram. So in order to reduce 50 gram of the reactant into its half, that is 25 gram, there will be some time will be taken, and that time taken will be half-life period. Okay, if you take initial amount as 1 gram, then what is the half of your 1 gram? It will be 1 by 2. So that 1 by 2, in order to reduce from 1 gram to 1 by 2 gram, and that time will be known as half-life period, and it is found that half-life period T half is equal to 0.693 divided by K. Thus, half-life period for a fast order reaction is independent of initial reactant, that is your R naught, but is inversely proportional to specific react constant K. So from the above expression T half equal to 0.693 divided by K, we found that half-life period is independent of R naught, but is inversely proportional to specific react constant. So it may be asking in your examination in different ways. Either it may ask in your assertion or reasoning type question, or it may be asking in your multiple choice type question, or it may be asking in solving the numerical to determine the value of specific react constant K by giving the value of T half. In that case, you have to know this expression. Your expression is T half equal to 0.693 divided by K. Now, let us come to a very important term called temperature dependence of rate of reaction. And as we know, the rate depends on the temperature, and the temperature dependence on the rate of the reaction, it was discovered by a Swedish chemist called Svante Arrhenius in 1889, and this equation was given as Arrhenius equation, and this Arrhenius equation is an equation for showing the temperature dependence on the react constant of a reaction, and it was given as K equal to A, capital A into E to the power minus EA by RT. Let it be question number 1, where small k, it is the specific react constant, and EA is activation energy. So this activation energy, it is asking in your examination. My dear student, you have to know the definition of activation energy. I will be giving definition of activation energy. So activation energy is the minimum amount of energy of a molecule which is required to cross over the barrier height for forming products. So there is activation energy. So for example, let me just give a simple example. Now all of you are going to face CBSE examination. In order to declare you to pass the class 12 examination, you have to get at least 33% in aggregate in all the subjects. That 33% in aggregate in all the subjects in order to declare you are passing. And that 33% is your activation energy. Okay, and that is your minimum mark. Likewise, in order to form the product by combining the reactants together, some minimum amount of energy is required. That minimum amount of energy required for forming the product by the reactant molecule is called activation energy, and it is denoted by EA. And this definition of activation energy, please look into. And capital R is gaseous constant, T is absolute temperature, and A, it is a constant called pre-exponential factor or frequency factor, which is characteristic of reaction. Taking log of both sides, we have ln K equal to ln A minus EA by RT. So if we plot a graph, see, graph of ln K along y-axis and 1 by T along x-axis. See, you will get a straight line. So it is in the form of y equal to minus mx plus c. Y equal to minus mx plus c. So here your slope is minus EA by R, because EA is activation energy. It is a constant quantity. R is also a constant quantity. So EA by R togetherly, it is a constant quantity, and this will be your slope. So your slope will be minus EA by R, and intercept will be ln A, ln of your pre-exponential factor. So if we plot a graph of ln K versus 1T, we shall get a straight line with a slope of EA by R and an intercept of ln A as shown in figure. So this nature of the graph, okay, this nature of the graph you have to keep in your mind, and from this we may able to find the value of activation energy from slope, and we may also able to find the value of capital A pre-exponential factor from intercept. Because from intercept, from the graph you can find out the intercept. You measure the value of your intercept with the help of a scale from the graph, and take the log of the intercept. There will anti-log of the intercept will give the value of A, which is pre-exponential factor. If small k1 and k2 are their constants at T1 and T2. Capital T1 means it is initial temperature, and another is your T2 at another temperature. Then log of K1 equal to log log A minus EA by 2.303 R T1. Let it be question number 3. Similarly, log of K2 is equal to log A minus EA by 2.303 R T2. Let it be question number 4. So now 3 minus 4 gives log of K2 minus K1 is equal to EA by 2.303 R T1 minus EA by 2.303 R T2, implies to log of K2 by K1 is equal to EA by 2.303 R first bracket 1 by T1 minus 1 by T2, and further equal to EA by 2.303 R third bracket T2 minus T1 divided by T1 T2. So this equation number, let it equation number 5. So my dear children, this equation number 5, that is log of K2 by K1 is equal to EA by 2.303 R 1 by T1 minus 1 by T2, or EA by 2.303 R T2 minus T1 divided by T1 T2. So this equation you have to keep in your mind for finding the value of activation energy. Okay, so this formula you have to keep in your mind for numerical problem. And now see, I'm just arranging some practice question. Practice question. Are you listening me, my dear students? Are you listening me? Hello, my dear students. Are you listening me?
Sir, GNB
Yes, audible.
Yes, any problem? I'm just bringing some practice questions. See, calculate the overall order of the reaction which has the rate expression. Number 1, number A, rate equal to K, concentration of A rise to the power 1 by 2 into concentration of B rise to the power 3 by 2. Next, number B, rate equal to K, rate equal to K, concentration of A rise to the power 3 by 2 into concentration of B rise to the power minus 1. So here two rate law expressions are given to you. Now we are going to determine the overall order of the reaction. So from the reaction, from this rate law, we clearly observe that there are two reactants on both the reactions. The two reactants are capital A and capital B. And for determining the rate of the reaction, rate law are given as given in A and B. Now we are going to find the overall order of the reaction. So can anyone tell me for reaction number A, what is the power of reactant A? Yes. For number A, what is the power of reactant A? Yes, anyone? Yes, anyone? Yes. What is the power of reactant A? Yes. The power of reactant A is half, and for the reactant B, the power is 3 by 2. So that's why now let us see what will be the answer. Your order is equal to half. Half means the first half comes from the power of reactant A plus 3 by 2. 3 by 2 means it is the power of reactant B. So you have to take the sum of half and 3 by 2. So here you have to take LCM. Your common factor is 2. If you take your common factor is 2, and then by adding together, you will find S2. So if the order is 2, then the reaction will be of second order. Okay. Now let us come to for the number B. So in the number B, rate law, rate equal to K, concentration of A rise to the power 3 by 2 into concentration of B rise to the power minus 1. So order equal to, for A, reactant A, what is the power? For reactant A, the power is 3 by 2. So 3 by 2. Then for reactant B, the power is minus 1. So you have to take the sum of these two. That is 3 by 2 minus 1. So 3 by 2 minus 1 is half. So if the order is half, means half is not a whole number. So it is called a fractional order. Okay. Now Let us see one more question. Identify the reaction order from each of the following rate constants. So here the value of rate constant for two reactions are given in number A, K equal to 2.3 into 10 to the power minus 5 liter mole inverse. And number B, K equal to 2.3 into 10 to the power 5 second inverse. Now let us see what will be your answer. Your answer is second order. Number A is second order. Why? Because our formula is K equal to concentration 1 minus N. So here N is your second order. If N is 2, then it will be in the form of liter mole inverse. Next, number B, second inverse. Second inverse is in the form of time inverse. So that's why it is of first order reaction. Can you hear me? Hello? Now, I am just collecting some.
Yes, sir.
I am just collecting some simple two questions adopted from your practice question paper, which was published by the CBSE. The first question is, a first order reaction takes 77.78 minutes for 50% completion. So, can you tell me what is the meaning of this sentence? Yes? What is the meaning of this sentence? A first order reaction takes 77.78 minutes for one. The meaning of this sentence is the value of T half. There is half-life period. Okay. 50% completion means T half-life period. So the value of T half, it is given as 77.78 minutes. Then calculate time required for 30% completion of this reaction. So for this, the value of log 10 is given as 1, and the value of log 7, it is given as 0.8450. So how to solve this question? So first of all, in order to solve this question, so you have to use the first expression. That is your K equal to 0.693 divided by T half. Okay. From that, your K equal to 0.693 divided by T half. So you substitute the value of T half as 77.78 minutes. From there, you will get the value of your K. Okay. From that value of K, by knowing the value of K, you just use the formula, your simple formula for integrated fast rate equation. What is our formula? Your formula is T equal to 2.303 by K log of R naught by R. Log of R naught by R. Okay. So log of R naught by R. So your R naught will be your 100. Your R will be 30% completion. So if it is 30% completion, what will be the value of R? The value of R will be 100 minus 30. What is the value of 100 minus 30? What is the value of 100 minus 30? 70. Okay. So take log of 10 divided by 70. So log of 100 divided by 70 means if from 0 of 100 and 10 of 70, you will cut. So that's why log 10 divided by log 7. So log 10 value is given, log 7 value is given. Substitute the value, do the simplification, double to get the value of the time required. It's the way how you are going to calculate the time required for 30% completion of the reaction. It is very easy. Okay. So for solving this, you have to use the concept of formula, that is your T half equal to log of R naught divided by R. These two formulas you have to use for solving this question number 1. Okay. Now let us come to the question number 2. What is question number 2? Define pseudo fast order reaction with an example. So I have already given pseudo fast order reaction. So what is pseudo fast order reaction? Yes? Can anyone tell me what is pseudo fast order reaction? Pseudo fast order reaction, they are the reactions where the reaction follows fast order, though it contains more than one reactant molecule. Or simply, you can also say that pseudo fast order reactions are the reactions following fast order reaction, though it contains more than one molecule. Okay, and I have given 2 examples. The first one is inversion of cane sugar, and second one is hydrolysis of methyl acetate. Okay. Okay. Thank you, everyone. Thank you. Thank you. Khuất lâm à? Hai cái lâm nhiều. Stop streaming thôi. Xin lỗi đi thôi. Mình thông qua. À. Mình xin lỗi ghé. Xin muốn tàu bên đó. Rõ. Kita menu oknum. Chỉ số lùi sẽ upload từ giờ về sau thôi đã.
Complete na?
Ha sir. Thank you sir. Thank you everyone for attending to this my online class. Thank you everyone once again. Again, you can see. Yeah. Dạ. Betul kah? Masih hay kita tahu betul sah. Amda kalau amda slide amda sembih ay belum siap ke sebab pertumbuh tu. Sekarang tu perantian. Ha. Kare. Isi hari masih jauh ya. Mungkin saya feedback kamu tarik ni. Feedback tu mungkin feedback tu mungkin ada. Yang mana cara saya phone tu dia awal. iPhone tu sah.